Okay, guys, so today we're going to talk about the formal definition of limit. Again, depending on the book you're using, some books call this section 2.4, some books call this section 2.7. I believe for the class I'm teaching right now, currently for this video, it's 2.7, but just keep in mind what's important is the formal definition of limit, the title of this section, okay? So, suppose we're given some f of x, and we're going to say that this f of x equals 5x minus 1 when x is not equal to 1, and it's equal to 5 when x is equal to 1. So we're dealing with a piecewise function, okay? So we want to find out how close can we get to 1, okay, to make sure that we're within a certain value of 4, okay? So, let's see how can I talk about this? But what if I wanted to know how close do I have to take x values so that my y values will stay within, let's say, 0.01 or 0.001 or 0.001? Because remember when I talked to you guys about this, I walk from the left and the right, correct? And notice that it always says arbitrarily close to x. Well, how close to x? How close to 1 in this case? How close do I have to get to 1 that gets me close enough to 4? So it's kind of like you think of it as a game. Like somebody's going to say, okay, I want you to be able to get within, 0.005 of the correct answer. And you say, well, I can do that as long as you get me within 0.00008 of the x value. So it's like you're playing a game, but then couldn't somebody else come along and say, well, you know what? I don't want to be within 0.005 anymore. I want to be within 0.0000008. And then somebody could say 0.02 and then 0.007. So people could keep changing their mind, but you want to be able to get as close to the true limit as you want, right? So what we're going to do is we're going to say, let me see how we can talk about this. Let's first say we know the limit, okay? So we know, you know what, I want to write this in blue. We know the limit as x approaches, let's say 1, of f of x is equal to 4, right? So which one of these would I use as I get close to 1 but don't touch? Well, that would be this one, right? So I would do 5 times 1 plus, or 5 times 1, which is 5, minus 1, which is 4. So what we're saying is we already know the limit, okay? But how close do I have to get to 1 to stay within a certain closeness to 4? And again, the answers you always hear is infinitely close and so on. So we kind of want to expand on that, okay? So, and always keep in mind too, if you want to talk about a distance, I don't really care if you're above or below. I just want to know how far away. So a lot of times we'll use absolute values. So some kind of ideas that we want to keep in mind from limits is the absolute value of x minus a is less than delta. So this is the symbol for delta. So if I want to talk about this absolute value, I could rewrite this absolute value as negative delta less than x minus a less than delta. So that's how I could, I don't want to say undoing, but that's basically how we can get rid of the absolute values and turn it into a compound inequality. And then if I wanted to solve for x, I could just add a to all the sides. So then I would have a minus delta is less than x is less than a plus a delta, okay? So let's see here. The big question is, but how close to x equals 1 do we need to stay so that our y value stay, and in this case, I think we want to try 0.1, stay within, and then for each problem, it'll change, stay within 0.1 of 4, okay? That is to say, how can we choose delta so that the following is true? So this is kind of the gist of it here. It says if, let me write this in red because this is important. 0 is less than the absolute value of x minus 1 is less than delta, then the absolute value of f of x minus 4 is less than 0.1. Yep. Okay. So now here's the idea behind it, you guys. Here's the idea. So we're basically saying, notice this is x minus a, and this is f of x minus L, okay? So whenever you subtract two things like this, right? If you subtract two things and you subtract an x and an a and their difference is smaller than delta, then that means you're saying the distance between these two things, or the difference between x and your a value, is less than some delta. And again, we're trying to think small here. So we're thinking this is going to be some small number, okay? Now over here, we're saying that f of x minus L, well, isn't f of x just the height of the graph? And L is just the limit of the graph. So they're saying that they want the actual height of the graph and the limit of the graph, when you subtract them, to be smaller than 0.1. Well, that means that they got to be pretty close together. So if I said, well, I have $10 in my pocket and you have $9.90 in your pocket, the difference between us would be 0.1, right? So that's what they're saying, is that we're pretty close. $9.90 and $10, we're pretty close. But is that really infinitely close? Not really, right? Couldn't we use 0.00001 to try to, start being a little bit more realistic about approaching infinity? So 0.1 is a nice number, but normally epsilon is considered a very small value, okay? But in this case, we're just going to work with 0.1 because it's easy to calculate and we can see it on the graph. So what I want you guys to do is I want you to associate delta with the x-axis, and I want you to associate, we're going to call this epsilon, with the, associate with the y-axis. So what this means is it's like you're playing this little dance. We're hopping back and forth trying to get closer and closer to 1, and then the epsilon, and this is our deltas down here, and then the epsilon is getting closer and closer to 4, right? So that's what we're trying to do, okay? So they're now saying we're building this like window, right? So we're going to build this window and we're going to go up and down. We want to be within 0.1 because they said we want to be within 0.1 of 4, right? Because right here it says f of x and 4. This is the height of the graph. This is the limit of the function, okay? And we want the difference between them to be smaller than 0.1. So what I'm going to do is I'm going to go up 0.1, so this would be 4.1, and I'm going to go down 0.1, and this would be 3.9. And I'm going to do a little, like little mapping over to here, and then this would come down to here. And then I'm going to do another little mapping over to here. And again, this is a human drawing. It's supposed to be equal distance because they're lines, right? And lines, it should be equal distance. So this should be more realistically like right there, right? Oops. So now we need to figure out what is this number and what is this number. And that'll tell us what we need to do in order to get within a 0.1 of our epsilon. So basically what we're trying to decide is how can we choose delta that will promise that we'll be within 0.1 of our actual height, okay? So what we do is we do a little scratch work. We say 5x minus 1 is equal to 4.1, and 5x minus 1 is equal to 3.9. So all I did was I took my two values and I set them equal to the function so I could find their heights, or I could solve the equation. So all I'm going to do is I'm going to add 1, add 1, add 1, add 1. So now I have 5x equals 5.1, and I have 5x equals 4.9. Divide both sides by 5, by 5, by 5, by 5. So we should get, for this first one, x equals, if we plug this in our calculator, we should get 1.02. And here, x equals 0.98, I believe. Correct. Okay, so we have these two. So now what we're saying is that instead of having question marks here, I actually know these numbers. This is actually 0.98, and this is actually 1.02. Okay, now I want you to think about this. How far did I have to walk to go from 1 to 1.02? And how far did I have to walk to go from 1 to 0.98? I had to walk a distance of 0.02. So that means delta is worth 0.02. So I have now found my delta, right? How far away from 1 am I? I'm a distance of 0.02 away. So what that's telling somebody is if they want to be within a 0.1 of how close they need to be to 4, well, then you got to give me a delta that's within 0.02, right? Give me a delta that's within 0.02, okay? So that's what you do is you solve these little equations for the error that I shouldn't say the error, for how close they want to be to the limit and the function, how close they want them to be together, okay? So let's take a look at going a little bit further here, okay? So now let's say that they don't tell you how close they want to be. So I'm going to draw the same graph, and they just say, well, here's 4. And they just say, I want you to be within an epsilon. Oops. So, oops, I can't draw it like that. Well, I'm going to draw it, and you guys get the idea. There's an actual hole right there. There's a hole in the graph. Nah, it's not going to work. And then up here is 5 somewhere, but that doesn't come into play too much for us right now. Okay, so what they're now saying is here at 1, what if somebody asks us if 0 is less than the absolute value of x minus 1 is less than delta, then, or they state this to us, then f of x minus 4 is less than epsilon. So what they're doing is they're kind of messing with us on this. They're basically saying, okay, so fine, you found out that you have to set your delta to be less than 0.02, and that'll get you within plus or minus in this window of 4. Well, then they're saying, well, what if I don't tell you how close I want you to be? Because couldn't somebody say, well, 0.01 or 0.1 isn't good enough, I want 0.001. And then somebody else could say, oh, that's not good enough, I want 0.00001. So everybody could keep changing how close to 4 they want to be, and you'd always have to build a new delta that could get you to within that closeness. Now, here's the thing. If they could always build or get closer and closer to 4, but you could always find a new delta to get you closer and closer to A, well, then you're basically doing your job. You're showing them that no matter what they pick, you can always pick a delta to get you there. And that's what the limit definition of, I'm sorry, not the limit definition. That's what the formal definition of a limit is talking about, is it's telling you that no matter how close they want to get, you can get them there. And we'll kind of expand on that a little bit more in a second. So what we're doing this time is we're letting this distance. So we are, you know what, let me write this in blue. We are letting the distance from 4 vary, right? And we're going to say, or let's say the distance from 4 be a variable. Let's say epsilon, okay? Okay. Could we solve for the distance from x equals 1 in terms of epsilon. That is to say, could we find a delta such that this is true? Okay, so what we're going to do is we're going to come over here and we're going to try to work with this problem. We're going to say, can we find this question mark here? Let me do this. And again, it should be better than this, guys. I'm sorry, it should be perfect, but it's not. I just can't draw. Could we find these two question marks? Okay, could we find these two distances away from 1? So we're going to do just like last time. We're going to say 5x minus 1. So this is what we want to know, this guy and this guy. And then we want to know what the delta would be. So we do 5x minus 1 equals 4 plus epsilon, and 5x minus 1 equals 4 minus epsilon. Okay, so once again, I'm going to solve, and I get 5x equals 5 plus epsilon. I'm going to divide by 5, divide by 5, divide by 5. And this would give me x equals 1 plus epsilon over 5. This one would be 5x equals 5 minus epsilon. Divide by 5, divide by 5, divide by 5. So this would be x equals 1, minus epsilon over 5. So now here's the thing. That means that this is 1 plus epsilon over 5, and this is 1 minus epsilon over 5. But what's this distance from here to here, and this distance from here to here? That's epsilon over 5. That's, that distance is epsilon over, and they're the same because this is a line. Lines always will have the same distance, but other shapes, you know, like radicals or you know, polynomials or things like that will have different values, but we're not going to work too much in this class on that. But that means that this is, you could call this my delta 1, and you could call this my delta 2, right? But they're actually the same value because it's a line. Sometimes one will be bigger than the other, but in general, with lines, you're going to have them equal the same, okay? So that means we now can answer that question. If 0 is less than the absolute value of x minus 1 is less than epsilon over 5, if it's worth epsilon over 5, then I can get you, minus 4 is less than epsilon, okay? So whatever distance you want, I'm just going to divide it by 5, and that'll guarantee me that I can be within this window right here. See, I'm creating like this window that guarantees I can get you to any distance in there within a certain value that you wanted. You want to be within an epsilon of 4, right? You want to be within an epsilon of 4 right here. Well, no problem. As long as you let me use 1 minus epsilon over 5 and 1 plus epsilon over 5, I'll always get you there. I'll always get within that distance. So whatever you choose, so let's choose the previous problem, right? So in the previous problem, we chose epsilon to be 0.1, right? So if we take 0.1 and we divide it by 5, guess what we get? 0.02, right? All you do is you just take, you know, 0.1 and you divide it by 5, and we get 0.02, okay? Well, what is this worth? What is that equal to? We'll look up here. It was delta. So now what I've done is I have now generated a way to find any delta. In this case, they told me that epsilon was 0.1, or I should say in the previous problem, they told me that epsilon was 0.1, so my delta had to be 0.02 or smaller, right? So yeah, my epsilon had to be, my delta had to be 0.02. So basically what I'm saying is you pick any number. What if you pick 0.071, right? Well, I'm going to divide it. So say you choose this to be your epsilon, I'm going to divide it by 5, and I'm going to take 0.071, 0.071 divided by 5, and that'll be 0.0142. 0.0142, that will be my delta that I need to get within a 0.071, okay? And that's what you're doing, is somebody's telling you how close they want to be to the actual, they want the distance between the limit and f of x. And again, maybe I'm not iterating this enough, or maybe I'm not explaining this enough, but when you take the height of the graph minus the limit of the graph, and that distance is less than a small number, right? When you're subtracting these two things, when you're subtracting these, aren't you finding out how far apart they are from each other? And what you're saying is, how far apart is the height of the graph and the limit of the graph, okay? Well, you're saying that whatever that distance is, however far apart they are, positive or negative, we don't care, it's gonna be less than an epsilon. But don't we already say that epsilon's assumed to be a small number? So when the distance between two values is very small, okay, wouldn't you start saying that those two values are becoming the same? They're lining up, you know. So like if I'm 6'5" and you're 6 foot, then our distance between us is 5 inches. But if you're 6'4" and I'm 6'5", then our distance between us is 1 inch. And then if we keep adjusting, right, we keep saying, well, I want to be closer and closer and closer. Eventually, we'll both be so close to 6'5" that the distance between us is 0. There is no distance. So the epsilon delta proof, or the epsilon delta definition of limit, is basically saying that you can continue to get closer and closer to the true height of the graph, where the limit of the graph and the height of the graph become so close together that when you subtract them, the difference between them is less than epsilon. And how small can epsilon be? Well, epsilon can be the smallest number you could ever think of. And you're saying that I could still find a delta to make that work. So that's kind of the idea and the reasoning behind the epsilon delta definition of a limit, okay? So let's try a formal one, okay? Let's try one from scratch. So this is a problem you might see, okay? And again, we're gonna try to work with some of the nicer ones, okay? So let's say, prove that the limit as x approaches 2 of 2x plus 1 equals 5. So they're telling you the limit, we already know the limit is 5. So you're not trying to find the limit, you're trying to prove that the limit is 5 using the formal definition of limits. So in order to do that, I need the formal definition of limits. So let's come over here. The formal definition of a limit. Okay, so it says let f of x be defined on an open interval that contains a except possibly a itself, okay, then the limit as x approaches a of f of x equals L if for all epsilon greater than 0, there exists a delta greater than 0 such that if 0 is less than the absolute value of x minus a is less than delta, then the absolute value of f of x minus L is less than epsilon, okay? So this is kind of the caveat of it right there. That's kind of the everything. Now, the way if-then statements work is I need the if statement to be true. You got to give me the if, then I can show you the then, okay? So you got to give me the if. So you have to assume that the if is true in order to give the then, right? To show the then. So what we're going to do is we're going to have to kind of work with this in a special way, okay? So I'm going to work with this problem now over here. And so this is something you guys you have to either memorize or have written down. This is the formal definition. This is the epsilon delta definition of limits. This is how you can prove that a limit exists, and it is this value. So again, we already know that the limit is 5, so it's not about that, okay? So what I'm going to do is I'm going to first identify a few things. So I know here that A is worth 2. I know that, what else we got here? We know L is worth 5, right? We know f of x is equal to 2x plus 1. And let's see, let's plug in what we know, okay? So we're going to take this information and we're going to use this formal definition of limit, okay? So let's see here. We have if 0 is less than the absolute value of x minus 2, oops, right? So x minus a is less than delta, then the absolute value of f of x minus 5, oops, is less than epsilon. Okay, so a common mistake students make is they just say, boom, it's less than epsilon because I said so. You can't do that. You actually have to show it. You have to show it happening. Okay, so that's what I'm going to teach you guys how to do. Okay, so we're going to need to find a delta that will make this work. So first, we need delta. Okay, so let's see here. Let's see. So what I'm going to do is I'm going to take f of x, which is 2x plus 1, and I'm going to set it equal to the limit, which is 5 plus an epsilon, and 2x plus 1 equals 5 minus an epsilon, right? So that's what we did in the previous problem. 2x plus 1 equals 5 minus epsilon, and 2x plus 1 equals 5 plus an epsilon. So I'm going to solve once again, minus 1, minus 1, minus 1, minus 1. So we get 2x equals 4 plus epsilon, 2x equals 4 minus epsilon. Divide by 2, divide by 2, divide by 2, divide by 2, divide by 2. Okay, so we got that. So now this becomes x equals 2 plus epsilon over 2, and this becomes x equals 2 minus epsilon over 2. So we can see obviously that delta is worth epsilon over 2. Now again, it's not a coincidence. You notice that here I got a 2, and this is a 2. That's not a coincidence, right? That's what we're working with here, okay? So remember, what we are basically saying is 2 plus a delta and 2 minus a delta. And that's how, remember, on the x-axis, if let's say that this was 2, we're going to walk to the left and we're going to walk to the right, and then we're going to find our value here, and we're going to find our value here, right? So that's what we're doing here. This is 2 plus delta and 2 minus delta, but we've actually solved for delta in terms of epsilon. It's epsilon over 2. So now we have to do the actual proof, okay? So proof, okay? So what we've done here is all we've done is we found what delta needs to be to make this work. Here's the actual mathematical proof. This isn't, this will be hard to show if you're doing online homework, but this is the idea behind it, okay? So we're going to choose epsilon greater than 0. And again, that means it could be anything, but as long as it's positive. And we're going to let delta equal epsilon over 2, right? So now we can say if the absolute value of x minus 2 is less than epsilon over 2, we have the following. So you guys, again, remember, we need the beginning statement. We need the if statement to be true. We need to say this is true so we can build from that now, okay? So if you give me this, I'm gonna be able to find and get you as close as you wanna be. We have the following, okay? So I'm gonna take the absolute value of f of x minus 5, okay? But then that means, didn't we say f of x was 2x plus 1? So that means the absolute value of 2x plus 1 minus 5. but that's actually equal to the absolute value of 2x minus 4, right? But I could actually factor out a 2, so this becomes 2 times x minus 2, and you'll see why I want to do this in a second. And this actually, the absolute value of 2 is actually just 2, so we can rewrite this as x minus 2 like this, okay? So all I've done is I've turned this into this by taking out the 2, okay? It's not going to change anything because the absolute value of 2 is still 2. Now the thing is, does this look familiar? Does this x minus 2 inside of an absolute value look familiar? Well, if we come over here, didn't we say that x minus 2 is less than epsilon over 2? So I now know that, now here's where you got to be a little careful, okay? I know that x minus 2 absolute value is less than epsilon over 2. I know that fact, right? But the problem is there's a 2 in front of that, okay? So then I have to put a 2 over here to counterbalance it, okay? So here's the thing. I'm going to say, and I should get rid of this equals, I'm going to say that 2 times the absolute value of x minus 2 is less than epsilon over 2. Now that would actually be incorrect. So think about this real quick. Pretend for a minute that this 2 wasn't there. Would that be a true statement? Yes, it would, because we said if this is true. So that would be a true statement. But the problem is that it's not just absolute value of x minus 2, it's 2 times the absolute value of x minus 2. So then I have to match that with a 2 times here. Now the inequality will still hold. You see that I want to make sure that this less than symbol right here will stay less than. If I do not put the 2 over here, I cannot guarantee it. I cannot guarantee that this is going to stay less than, okay? Because 2 times this may not be less than this anymore. But if I were to cover this up, that is definitely true. So if I uncover it and then match a 2 over here, I know that the inequality is still less than. However, what is 2 times epsilon over 2? That's just epsilon. So now you kind of got to follow I often talk about this as follow the bouncing ball, okay? Now think about this. This is worth epsilon. This is less than epsilon. And this is less than epsilon. And this is less than epsilon. And this is less than epsilon. That means this is less than epsilon. But weren't we trying to show that f of x minus 5 is less than epsilon? We just did it. So if the absolute value, if 0 less than the absolute value of x minus 2 is less than epsilon over 5, then, or epsilon over 2, epsilon over 5 was the last problem, sorry about that. Then the absolute value of f of x minus 5 must be less than epsilon. I showed that, right? Right? I just showed that this is equal to this, 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 but this is less than epsilon. So that means that the original is less than epsilon, which was what I was trying to show all along, okay? So that is how you prove it. So you start off with the function, and you have to end up with an inequality that is less than epsilon, because that's the original formal definition right here. F of x minus L must be less than epsilon, okay? So I just showed it for that problem, all right? And I showed it for any epsilon, right? Because epsilon could be any value. So it could be 7, it could be 2, it could be 3, it could be whatever, okay? Let me see how much more I want to go into that. Let me give you a slightly different one. So sometimes we're not dealing with lines all the time. That was a line, and in general, lines are very easy, and both sides will always be the same delta, okay? So now let's try something else. Let's say if f of x equals the square root of x minus 1, what delta will make the following statement true? If 0 is less than the absolute value of x minus 5 is less than delta, then the absolute value of f of x minus 2 is less than 0.3. So this is very similar to the previous problem, or the very first problem we did, where they're actually telling you epsilon. We know that epsilon is worth 0.3. We know that the limit is worth 2, and we know that a is worth 5, right? And I'm just taking that, here's a, here's the limit, here's epsilon, okay? So I'm just taking that from what I know about this formula and where everything is located at. So you can either draw a picture if you'd like. You know, it's really up to you. I think I'll draw a picture for this one. And I'll draw some square root function like that. And then let's have it be right about here. Oops. Let's have it be right about here is 2. And then remember, epsilon is 0.3, so we're going to go up 2.3 and we're going to go down to 1.7, right? And then that means, let's see here. So that is going to be, we know that this limit is already 2, right? Because they told us the limit was 2. And then we need to find these guys. I need to find this question mark. And I need to find this question mark. Now, again, normally when it's lines, it's just bad drawing, but it actually appears that this distance here is further than this distance here. And it is actually true this time because this is a square root function. You know, this is not a line function, so or linear function. So coming from one way or the other might change things. So what I'm going to do is I'm going to solve. I'm going to say the square root of x minus 1 equals 2.3, and I'm going to say the square root of x minus 1 equals 1.7. I'm going to do the plus delta and the minus delta, right? All I'm doing is I'm solving for these guys right here, okay? Just like we did before. So now I'm going to square both sides. So I have x minus 1 equals, so I forget my calculator. Well, let's do 2.3 squared. So I get 5.29. So I get 5.29. All I did, by the way, guys, is I just squared both sides. So then now I add 1. So I have x equals 6.29. And then over here, I have 1.7. I'm pretty sure that's 2.89. So x minus 1 equals 2.89. And then add 1. So x equals 3.89. Let me double check if that's right. Yeah, that's right. Okay, and once again, all I did, you guys, was I squared both sides. Okay, so I have my question marks. So that means that delta, okay, so let me write this here. So this is 3.89 and this is 6.29, okay? So what we want to do is we want to see which one, did I write 5? Why did I write 5? Hold on, you guys. This is not 2. This is 5, right? I messed that up. So this is a 5 right there. Sorry about that. Please fix that back in your notes. Okay, so what I'm going to do is I'm going to see how far from 5 I am here, and I'm going to see how far from 5. All right, I'm trying to find this distance from here to here and this distance from here to here. So let me call delta 1 5 minus 3.89. Let's just call it my absolute value because I just care about the distance. So that's 1.11. And let me call my delta 2 6.29, or I could do it absolute value of 5 minus 6.29, because again, all we care about is how far, and that would be 1.29, okay? So I have two deltas. I have delta 1 and I have delta 2, okay? So when you're dealing with this situation, you always take the minimum delta, the minimum, and it depends on how you want to write it, of delta 1, comma, delta 2. So in this case, we take delta 1, which equals 1.11, because that is actually closer to 5 on the x-axis. Because remember, we're trying to guarantee that we're going to be within a 0.3. So look here, if I go over this distance here, when I walk up and I do this distance, if I walk over this same distance, that'll be here, and I'll walk up. You know what, I should do it in a different color. This distance from here to here, I'm trying to mirror it. It'll be about the same distance. It'll actually be from here to here. So notice I will not be within 0.3. This one will be fine. I'll be within 0.3 of the top one, but I'll be a little bit outside of 1.7. I'll be like at 1.5 or 1.6. So you always choose the minimum delta. So in this case, I'm going to choose the smaller delta to kind of be a little bit more cautious and err on the side of caution. Okay, so this is a case where they gave us epsilon so we could actually find the delta. If they don't tell you epsilon and they just give you epsilon as a variable and they just say find it for all time, well then your answer will also be a proof, okay? In this case, they didn't want a proof, they just wanted us to find the delta that would guarantee it. In the problems where they just give you an epsilon, normally they want you to prove the limit is this by getting closer and closer and closer with delta, and that gets you closer and closer to epsilon, or I'm sorry, closer and closer to the actual height of the graph. When the actual height of the graph and the limit of the graph are so small that when you subtract them, their value approaches 0, that means that they're becoming the same thing. So that's the idea behind it. So think about this statement. When you say f of x minus L is less than any epsilon you come up with, couldn't epsilon be very, very small? So when you subtract two things and the difference is smaller than the smallest value you can think of. Now, this is not like actual math. This is just us kind of summarizing. Smaller value you can, than the smallest value you can think of. And this is that oftentimes you hear arbitrarily close. Those two values are approaching the same value. Think about it. If I tell you that the difference in my height and your height is 0, is smaller than the smallest number you could think of, doesn't that mean that my height and your height are basically the same? That's what this is saying. That's what this statement is saying up here. The difference between the height of the graph and the limit of the graph is becoming so small that no one can tell the difference anymore. And when you can be smaller than a number that's very close to 0, that means that it's so small. That's the arbitrarily, the infinitely close. That's what all that is really saying. But that's going to do it for this video, guys. It's a little bit harder section. We're not going to go too crazy on it. It gets a lot worse than this. And if any of you end up taking advanced calc, I think this is one of the first things you start working with in advanced calc, but more complicated versions of what we're doing, where you'll have to choose minimum deltas. But that's going to do it for this video, guys. Thanks for watching.